So today we'll start the uh, our live discussion session 2. Uh, this is a live problem solving session for NOC 24 CY04. The course entitled Basic Thermodynamics, Classical and Statistical Approaches. Uh, very good evening to all. Myself Akash Gutal. I'm a PhD student from Indian Institute of Technology Jodhpur, uh, Department of Chemistry. So today we are going to discuss some problems. Before that, before going towards the problem, I would like to summarize what we have learned uh, last week. So, so we'll do a quick revision about what we have done last week. So last week we have learned about. So we will say it is a revision. So what we have learned last week is first is the real. We studied about the real gas, and virial equation. So in that we first have seen Maxwell Boltzmann distribution. Okay, and in this functional form is 1 by n dn by dv is equal to root m 2 pi kbt into exponential minus mv square divided by 2 kbt. So this is the functional form of Maxwell Boltzmann distribution, where we will find we discussed earlier the uh, dependence of this equation upon temperature and the mass of the gas. And after that, we have also learned about real gases in which uh, we have learned how it deviates uh, how the ideal gas deviates uh, sorry, how the real gas deviates upon from the ideal. And we discussed about what is the Z value, that is compressibility factor. So Z we called as compressibility. Compressibility factor. So how real gases deviates from the ideal gas? It shows this value of compressibility factor shows that gives us information about that. Then third thing is we have seen the virial equation. So in virial equation, uh, we have seen what is the functional form of this compressibility factor in terms of series expansion. For series expansion, suppose for volume, it is we z depend the equation in terms of volume, it can be given as 1 plus b v plus uh, volume is molar c divided by v square plus higher order terms. And same equation we can write in terms of in terms of pressure is 1 plus b dash p plus c dash p square plus higher order terms. So what we call these coefficients are these b c are the coefficients and called as second and third order like that coefficient. So here the important one is the B, which is a second order coefficient of in the virial equation. So next thing what we learn about the second order virial equation. Sorry, virial coefficient. Second order virial coefficient. So what is the functional form of second order virial coefficient is? It goes like this: 2 pi integration 0 to infinity 1 minus e raised to minus u r divided by kbt r square dr. So where u r is called interatomic, interparticle, or inter sorry intermolecular potential. So interparticle potential or intermolecular potential. And we have also seen that the what is the functional form of B uh, in terms of for the general real gases. So for a real gas, uh, which follows the van der Waals equation, for that gas, the value of B is, so in the for the real gas, this second order virial coefficient it's can be given as B minus A by RT. And what we found is that A is more important when uh, the temperature is low, and B is more important, or the uh, the value of capital B more depends upon the small b when there is we have temperature high. And as we know that uh, so after that we also seen what is the uh, van der Waals equation for real gases. So we know that the van der Waals equation for the real gases, so in terms of pressure we can write E is equal to nRT divided by V minus NB minus an square divided by V square. So this is the real gas equation. And what we discussed, this two coefficient B and A in the virial second order virial coefficient are nothing but these two constants A and B in the real gas equation or the van der Waals gas equation. And the next thing that we found, uh, when any gas, when any real gas approaches uh, towards the ideal behavior, at that time this uh, factor, the second order virial coefficient becomes 0. And we can say, and that temperature where the real gas behaves like ideal gas is called that TB, which is nothing but the boils temperature. So that boils temperature is actually we can find out by the above equation, which is nothing but keeping B as a 0, we'll find A by RTB, which is nothing but, so we can find the expression for TB, the boils temperature, is nothing but A by, sorry, I should write it here, which implies TB is equal to A by BR. Okay, so this is one of the important equation. So I need to add one slide here. Fine. So next what we learn is about heat and work. So what we learn about heat and work is that these two, heat and work, are called path functions. So path functions means their value depends upon the path we chose uh, to go to state 1 and state 2. So what we have learned is this heat is directly proportional to the change in the temperature. Also, heat is proportional to the mass of the given substance, and which, if you combine these two dependencies, we will get heat is proportional to mass into change in temperature. Okay, and when we remove the proportionality constant proportionality, then we will get a constant called specific heat. So see here called specific heat of the system. So how we define the specific heat is that the specific heat is defined in such a way that for a given substance, if you want to the heat needed to increase the temperature of the substance by just 1 degree, so that's called the specific heat. And per unit mass of that substance. So this is the definition of this specific heat, and then we move towards the first law of thermodynamics. So what first law says is that changing internal energy of the system is nothing but the heat gained by the system plus the work done by the system or on the system. So this is the first law. So this is also called conservation of energy uh, law. So this also implies the energy is conserved. So next thing can so after that we learn the concept of, I will change the slide. Let me add another slide. So the concept of total and exact differential. So how we define the uh, total differential is that suppose there is a function f of x f of xy. It depends upon two variables x y. Suppose change in that function, so change in that function is equal to small change in del by del f divided by del y, keeping x constant, into dy plus del f by del x, keeping y constant dx. So if your function obeys this equation, then it's called the total differential. And what we said about the exact differential is, suppose this equation I can write as m dy plus n dx, where m and m is del f by del y constant x, and n is del f by del x at constant y. And suppose, and the definition for exact differential is, suppose this change in m divided by change in x at constant y, it should be change in n by change in y to at constant x. So this is condition for exact differential. So what is general meaning of exact differential is nothing but, suppose if the change in the given function, while first changing uh, del x and then changing with del y, it should be same as that of first changing the, y and then changing x. So it means the same. So this uh, the order of the two, the change of order of the two should not affect the change, the change in the value of that function. So that is we called as exact differential. This equation implies the same. So what we know is that the state functions that we have, they are actually exact differentials, and what are the whatever the path functions are, they are in exact differential. So this is the mathematical definition for the state uh, functions and path functions. So we'll move towards the next, our first question. So you can uh, you can solve by yourself right now, right onwards. I'm giving some time to you, and let me know the answer. You try to solve it. I'm also at the same time I'm also solving. So you also try to solve the question and tell me the answer if you able to solve it. So the question goes like this: calculate the pressure exerted by 8.5 gram of ammonia contained in 0.5 liter of vessel at 300 Kelvin. For ammonia, the A and B values are given. You can type your answer. If you got the answer, then you can type also. It's okay to type. So we'll solve it. So we will extract the given things from this example. That the first thing is given is mass of ammonia gas, which is nothing but 8.5 gram, and containing a 0.5 liter of vessel. The volume is 0.5, and the temperature given is 300 Kelvin. The value of A is 4.0 atm liter square, mole rest minus 2, and B is 0.036 liter mole inverse. Okay, so when you say the A and B values are given, this is the this equation is related about uh, van der Waals gas equation. Yeah, Sangeeta got the answer 21.52. It's the right answer. Yeah, it's right. Fine. So we'll solve it quickly. Give me a minute. My pen is not working. So now the pressure is equal to nRT by V minus NB minus AN square by V square, according to van der Waals equation. So we just put it. So we need to calculate the N. What is the number of moles? So here we will calculate N is equal to the mass of the gas divided by its molar mass. The molar mass is actually NH3 is 17. So we'll get nearly 0.5 moles. So 0.5 into R we need to take in terms of liter rate, 0.082 into the temperature 300 divided by the volume is given that 0.5 minus 0.5 into B, 0.036 minus, yeah, it's 4 into 0.5 square. V is also 0.5 squared. Okay, so this will get cancelled. This also get cancelled. What we will get is 0.082 cross 300 cross. If you take 0.5 out, you can write like this. 1 minus 0.036. And this 4. If you calculate this part, then you will find it is nothing but 21.5180. So the next question is, the van der Waals equation for CH4 at low pressure is. So for CH4, what is the van der Waals equation for low pressure? Can you answer? So this is a CH4, the low pressure. What happens? I will give the hint. At low pressure, your molecules, the interaction between the molecules uh, become less. And the interaction term, even though it is less, but at low pressure, your volume is really high. Once the volume is high, uh, it happens that whatever the coefficient is there is the B value uh, is actually become negligible. Once it is become negligible, then we'll be having your real van der Waals equation will be, suppose we have the van der Waals equation like this, P plus A by square. Option is minus A by V, PV is equal to RT minus A by V. Yeah, right. It's option B. So what happens is V minus B is equal to RT. If you take this B, uh, becomes very much small, means negligible. You can neglect it at low pressures. If you go, the pressure is low, and because of that, we will have the equation P is equal to, we can, 1 second, RT by V minus A square. So if you multiply both sides by PV, you will get RT minus A. So here answer B. So the next question is, the compressibility factor for the gases is less than unity at STP and NTP. Based on that, choose the correct option. So we have given that compressibility factor for the gases is the less than unity. So we have Z is less than 1. For your information, the Z is, we know that P V by RT. So it is less than unity at given at the standard temperature and pressure, or normal temperature pressure. Based on that, choose the correct option. So what happened at if Z is less than 1, which means the PV part is actually becoming lesser than RT. So if the PV part is becoming lesser than RT, which means we know that the standard temperature and pressure, we know that in 1 mole of a gas occupies 22.4 liters. And for the this is for the ideal gas, it will occupy 2.4 liter at standard temperature and pressure. But we are having compressibility factor Z is less than 1. So once it is less than 1, which means the PV is actually must be less than RT to get the Z less than 1. So if PV is supposed to be RT in case of our ideal gas, but it is less than RT. If it is less than RT, which means that we can say this volume ideal. So at PV ideal is equal to RT. If we replace the RT, we can get the equation VI, and V is actually less than VI. So we can say V is less than 22.4 liter. So your answer must be uh, B. The fourth question is, suppose 1 mole of SO2 occupies a volume of 350 ml at 300 Kelvin and 50 atm pressure. Calculate the compressibility factor of the gas. This is simple. The same equation will apply here. Z is equal to PV by RT. So Z actually gives you the idea how your gas is deviating from its ideal behavior. So can you calculate? It's simple. Yeah. Sangeeta is right. Option A. So Z is equal to we just extract the given things. N is equal to 1, and we have the volume is 350 ml at 300 Kelvin. At pressure is 30 atm. So we just put the values 30 into 350 ml. You just take care of units. 0.35 liter should be proper divided by your liter atm R is 0.082 into 300, which if you calculate will give you 0.7113. Next question is, a system is provided 50 joule of heat. The work done on the system is 20 joule. What is the change in the internal energy? This is also simple. You just calculate. These are the general problems which just warming up. We will go for better problems after uh, 8th or 9th problem. So nearly we are going to solve 15 to 16 problems today. So these are just warm-up problems. It is simple. This is this problem related to the first law. 70, answer is right, 70. So quickly I will go. 50 joule is nothing but we know you are, sorry, 50 joule is D. Your first law is du is equal to dq plus w. So what you're having is you have heat is 50 joule plus your 20 joule is the work, nothing but the 70 joule your answer. Fine. So question 6, calculate the work done when 56 gram of iron reacts with the hydrochloric acid in a closed vessel of fixed volume. So this is also conceptual question. If you say calculate the work done when 56 gram iron reacts with hydrochloric acid in vessel of fixed volume. 0, right? Because closed vessel of fixed volume, if this volume is fixed, means there is no work done. You must remember, if the volume is fixed, then there is no work done. So next question is calculate the maximum work done in an isothermal expansion of 16 gram of oxygen at 300 Kelvin, occupying a volume of 5 dm cube until the volume becomes 25 dm cube. This is about the maximum work done in an isothermal expansion. This is the isothermal expansion. So I will extract the given. If you are able to calculate, you just put the answer in the comment section. Given things are uh, the mass of oxygen is given 16 gram and temperature is 300 Kelvin. And volume is 5 dm cube. That V1 is 5 dm cube and V2 is 25 dm cube. Let's quickly convert this 16 gram for oxygen. 16 divided by, we need to convert this, mass into number of moles. So number of moles will be 16 divided by molar mass of oxygen is 32.5. And the maximum, as we know, the maximum work done at the isothermal expansion is W is equal to minus nRT ln V2 by V1. So if you put the all the variables, it's 0.5 cross 8.314 as it is asked in joule, 8.314 R value into 300 Kelvin into ln 25 by 5. Can you please calculate and tell me the answer? Just calculate and tell me the answer. Yes. Yeah, you can take log if it is ln. It's actually the equation I've written is in ln, is natural logarithm. If you see, it's e. Okay. So if you want to take in log 10 basis, then you can include the 2.303 term. It's okay. Yeah, if you are having a calculator which is can calculate this ln directly in the natural logarithm, it will be fast. Your calculation will be fast. You don't need to include 2.303. Is it clear? If I have used the log 10 in the base as a base 10, then I need to include 2.0. Yeah, right answer. A. And the sign is must you must check the sign when you calculate the work. You can actually logically understand when the expansion is happening, which means your system is doing work, and your system is doing work, then the system is using its own energy, which means the energy, whatever it is going out as a work, so it must be a negative value. So like that we must understand, and we must take care of the signs in the answer. So now onwards I will include some competitive exam problems. Uh, so this is the question that compared to C2H6, the value of van der Waals constant A and B for helium will be. So options are both will be smaller, A will be larger, or B will be smaller. B will be larger, but A will be smaller. Both will be larger. So we have C2H6 and helium. This is asked in GATE 2001. Think about what is A and what is B. You'll get the idea. Uh, no C. No. Please try. Please try. So I will give hint. A is actually depends upon the interaction between the molecule, which affect the pressure, and B is nothing but your effective volume uh, of your given gas. So as we can see here, C2H6 is effective volume will be uh, really higher than helium. So it must be that B value. What should be what it should be? It should be smaller for helium. And in case of A, in case of A, the interaction between the molecules are more in C2H6, and than the helium. And because of that, A value is must be higher for C2H6, and A value must be lower for. Yes, yes, there is no interaction in helium. A must be smaller, and huh, B is actually because B is related to the total volume of only gas. So the total that volume of the C2H6, whatever it occupies is actually more than the helium. Helium will be small and this will be large. So B will be large for C2H6 and small for helium. So your answer must be A. Both will be smaller for helium. So this is the next question. One mole of an ideal gas undergoes a cyclic process A, B, C, D, A, starting from point A through four reversible steps as shown in the figure. Total work done in the process is. So we need to calculate the total work done in this process. So what we have given, you should keep in your mind that the graph is given about volume and temperature. Try to solve. Okay, fine, fine, fine. So we'll solve this question. So as we see that this the process is from A to B, then B to C, C to D, and D to A. So whatever we know that the work only happens when there is expansion. So what we know that so where the expansion is happening, you can have an idea about when we see this graph. If you see A to B process, sorry, A to B process, uh, there is increase in volume, and C to D process, it is decrease in volume. Okay, but if you see when B to C, there is a no change in volume, and D to A, there is a no change in volume. So what immediately you must understand that only you need to calculate the work for here, this part A to B and C to D, and add them, you will get the answer. So here must be work done by the system. Here must be work done on the system. So that is the uh, idea. So remember the temperature at A to B is T1 and C to D is T2. If you know, then your work done, as you know, is nRT minus nRT ln uh, V2 by V1. And in case this is for A to B, and work done at C to D is nothing but minus nRT ln V1 to V2. Why this form of work? Because it is, as we know, the T1, the temperature is constant, that this is isothermal, isothermal reversible expansion, because it is given that it is reversible steps. So this is the isothermal reversible condition. We can apply WAB, and if you add WAB plus WACD, the work between these two process, you will get, sorry, I just forget to add T1 and so what you have minus an RT T1 ln V2 by V1. And if you see, it is here V1 by V2. So we will change it. It will become plus an RT2 ln V2 by V1. If you change the, if you know the logarithmic law, that when we change the uh, this ratio, then we will get the negative sign outside. So what we get is, so N is 1 here, it's 1 mole of gas. So we'll get my, sorry, R into T2 minus T1 ln V2 by V1. So that will be your total work done. And it is at the option D. The next question is the van der Waals constant A and B of a CO2 are 3.69 liters square bar mole uh, raised to minus 2 and 0.04 respectively. The value of R is 0.083 bar dm cube mole inverse Kelvin inverse if 1 mole of CO2 is confined to a volume of 0.15 liter at 300 Kelvin, then the pressure in bar exerted by the gas is. So just try to solve this. It's again related to your van der Waals gas equation. I will write the given things first. If you if you can able to calculate it quickly, you can put it in the comment box. So we have given things A is 0.04. I forgot to write. This is also from GATE exam question. So value of B is, sorry, I just made a mistake. 3 point. So take care of the units and this is the numerical type question because you need to careful about the sign and the value. So we have van der Waals equation nRT divided by V minus NB minus A n square by V square. Let's put the things. 195 is not the answer. You just recheck your calculations. So n is equal to 1. Keep in mind n is equal to 1. 62.36 is the right answer. Yeah. The answer should be 62.36. and precise if you precise 364. So you must take care about the decimals also and the value that we you calculate along with its sign in case of gate examination. If you calculate it, you will get 62.364 bar. So this is just one of practice problem. Here is one question, question number 11. In the following setup, two chambers 1 and 2 are enclosed by a thermally insulated material. Chamber 1 contains an ideal gas at 100 atm. Chamber 2 is completely evacuated. The two chambers are separated by a breakable seal. Before the seal is broken, the temperature of the chamber 1 is T1 initial. Then the seal is broken and the gas is allowed to rush to chamber 2. The volume of the chamber 2 is 100 times the volume of the chamber 1. When the pressure in the two chambers become equal, the respective temperatures T1 final and T2 final, which of the following statement is true? This is asked in TIFR 2015 exam. This is just conceptual question. Yeah, evacuated means there is total vacuum inside. There is nothing in chamber 2 at initially. It's just conceptual question. Really, it's a really nice question in terms of concept. If you know it, the answer is quick. Take 1 minute more. You don't even need to write any equation to solve this question. Uh, no. Okay. I will explain the question. Uh, the question given is that this these two chambers are totally isolated and there is no heat transfer outside these two chambers, which mean and the chamber one uh, is having gas and this temperature is T initial. No, PV by T is not applicable here. I will tell one statement I will tell. You can give the answer. That statement is that The statement is that when the free expansion of the gas is happening, there is a no work done. Now you can give the answer. Let's check you can give the answer or not. When there is a expansion, free expansion of the gas, there is a no work done by the gas. Yeah, right. Right. Now you got the point. So your answer must be A. So here the question is built in a such a way that it creates the environment of being it difficult. But if you really see the question, it's only dependent on one concept is that the free expansion of any gas is have there is no work done by the free expansion. So whatever once the expansion is happen and the gas released to chamber 2, it doesn't any work, so it doesn't do any work, and which means that there is a no change in internal energy. So there is an according to the first law, and as it is a sealed totally sorry the totally the your system is isolated, which means there is a no heat transfer from any side. Because of that, when free expansion happens, your internal energy stays constant, and there will be no temperature change even the gas get expanded to the second chamber. So that's the answer, right? So next question. The specific heat of a certain material monotonically increases with temperature, and two identical blocks of this material are kept at 50 degrees Celsius and 100 degrees Celsius respectively. The two blocks are now brought in contact with each other. Assume that no heat is lost to the surrounding. When thermal equilibrium is reached after the two blocks are kept in contact, what would be the final temperature of the two blocks? This is also come in TIF, came in TIF for 2016 exam. And there is you can try, you can try and get, even if you get the wrong answer, it doesn't matter. Even if you get the wrong answer, you will learn from that. That's important. Learning is important, and doing these problems is actually gives you uh, more uh, conceptual clarity. TF can be either more than or less than 75 degrees Celsius, depending upon the precise variation of the specific heat with temperature. So that is not done, sir. No. Sorry. One thing I need to check. The answer is no, not C. Yes, this is. But it also really checks your means the concept related to the heat space specific heat, and uh, this question also you don't need to do any calculation on paper. So the question is actually gives you, suppose there is body A and B. Suppose there is body A and B, they're totally identical, means their masses are same, and the material also the same. And the first thing is given to you, the specific heat of the certain material monotonically increases with temperature. Whenever you see the monotonically is a word in your question, it means that your your quantity, or the whatever the the function is actually the specific heat and the temperature. The monotonic increase means the given function is actually increases. Monotonic increase means the given function increases when the temperature increases, which means there is the monotonically in the sense its functions value can become a flat and then increase, but it never decrease. Okay, so that you should keep mind, it never decrease. Monotonical increase means if you so that if you increase the temperature, the Cp stays the same or increases. So it goes like this, but it never goes down. That is the point. So if such a material is there where the specific heat always increases with the temperature, its precise term is monotonically increases with the temperature, then you have two blocks which is the 50 degree, A is 50 degree and second is 100 degrees Celsius, and we kept them in a contact, and they said that there is no heat loss to the surrounding. When the thermal equilibrium is reached after the two blocks are kept in contact, what would be the final temperature of the two blocks? If you see at 100 degrees Celsius, this material B should have higher specific heat. Specific heat of B, sorry, must be higher than specific heat of A. Fine. Which means when you keep this A and B in contact, then the heat will started flowing from B to A. And when it starts flowing, the decrease in the block, the temperature of a block B, suppose it sends one Q heat, it will increase this temperature of A uh, with uh, means the higher, in the sense suppose 1 degree decrease happen in this block B, it may increase the temperature of A with 2 degrees, because the CB, the specific heat of B, is greater than A. And because of that, if you see, suppose it happens 55 when 95, and if you see, uh, sorry, 90, 55, or we can say 60, and when the equilibrium is reached, whatever we having the difference between the two, which is 100 minus 50, so I think we're 75. When the system goes like this, then it will equilibrate with each other always greater than the 75 degree. So how as heat of B is high? Okay, fine. Uh, you are asking how the specific heat of B is higher than A. You are asking about this. Yes, it is. We have been told that in the first line that the specific heat is material monotonically increases. Suppose we having a certain arbitrary function of C specific heat with the temperature. Okay, certain oh, sorry, certain arbitrary increasing. Fine, and this is the 50 and this is the 100 degrees, suppose. So what you will get for this is for the same material. What you will get, this is for CB, and then we will get this is for CA. Fine. That's why we are saying that CB is greater than CA. But if you see again, this once this will increase, the temperature of A gets increased, then also it will follow the same function of Ca, and its Ca also get increased little bit. So in every step the heat transfers, it will change the Ca and Cb also. But for given certain temperature until the equilibrium come, this Cb is greater than Ca is generally maintained because your function of the specific heat is monotonically increases with temperature. And because of that, the equilibrium point will be uh, will be greater than the halfway between the two. Generally, oh sorry, greater than the halfway between the two, which is nothing but the 75 degrees Celsius. If this temperature dependence is not there for the specific heat, it it could have generally could have uh, stopped at the 75 degrees Celsius. But because we are having this monotonically increasing specific heat, it will end up the equilibrium temperature as greater than 75. Okay. The question is, an ideal gas occupies an unknown volume V liters at a pressure of 12 atm. The gas is expanded isothermally against a constant external pressure of 2 atm so that its final volume becomes 3 liter. The work involved for this expansion process is, in calorie they are asking. The rounded of the two decimal places. This is also a gate question. Forgot to write. Try to solve it. I will give you 2 3 minutes. So you should consider the first sentence is important, and the gas is expanded isothermally against the constant external pressure of 2 atm. Try to calculate it. So every information given in this question is important. So I will give you one hint. Uh, when you read the question for the first time, 113.6 scale, I just check the answer is just pause for one. No, the answer is wrong. Just uh, check your calculations again. Remember, this is not a isothermal uh, a reversible expansion. Okay, you just take care of that. It is not isothermal reversible expansion. This is isothermal expansion, but not reversible. It's irreversible. So you may have used this isothermal reversible W is equal to the same equation in RTL and V2 by V1. This will not work here. Okay, fine. We will solve this. So the ideal gas occupies unknown volume V liters at a pressure of 12 atm. So we are given that given gas occupies 12 liter at, suppose, say 1 V, uh, sorry, 12 atm pressure. It will occupies V liters uh, of volume, and the gas is expanded isothermally against the constant external pressure. So the external pressure that we are having is 2 atm, and whatever we are expecting the final volume that we are getting is 3 liters. The work involved in the expansion process is digest calorie. So what we are having is the given gas is actually at uh, occupies 12 atm pressure. Uh, sorry, 12 atm pressure as given volume V, and the external pressure that we are having is 2 atm. So here we can say that the external pressure, whatever the work that gas does, is actually happening against the 2 atm pressure. And as we know that, one second, pardon, my pen is not working. I just need 1 minute. Fine. Yeah. So we have uh, P1 is 12 atm, and the P2, the P external, is 2 atm. So the external pressure 2 atm when the expand what when the expansion is happening, so the final pressure become 2 atm, and the initial uh, pressure is 12 atm. So we have P1 V1 is equal to P2 V2. So what we can get, the volume V liters, that the initial of that gas we can get is P2 V2 divided by PV1. So the P2 is actually 2, uh, and your volume is 3 liter divided by P1 is 12 atm, 6.12.5. Fine. zero point 0.5 liter is the initial volume V that they are given is 0.5 liter. So what you need to calculate, you got the initial volume uh, and the final volume, then your work done is nothing but minus P delta V, final minus initial. Just calculate. Pressure is, external pressure is 2 atm, and V final is 3 minus V1 initial is 0.5 plus. So liter atm we are getting. So what we need to convert it into calories. So we can convert. So we can get the conversion factor here also 0.082. If it is 2 kilocal, 2 cal, then you can get, can you convert this in kilocal? Sorry, calorie, 5 liter ATM. We can convert is like this. 1, 2 is for 2, then for 5 is what? 0.082 into 2. 10 divided by 0.082, which is nothing but, can you calculate this? I can calculate. Okay. Yeah, 121.95 calorie. So as this is expansion, that value must be negative. And the answer is given uh, in the gate answer key is from minus 126 to minus 120. Fine. So your answer is coming as 121.95 is the answer. So what we need to consider here that it is the even it is the given as isothermally. Most of the times we will consider as isothermal reversible expansion, but it is not a reversible expansion. It is irreversible expansion because your gas is already having 12 atm, which is higher pressure than 2 atm. Okay, so when your gas get expanded, at that time that this 12 atm is far more than, oh fine, 2 atm. The next question is, on the basis of the ideal gas equation and van der Waals equation, the temperatures of a gas at pressure 10 megapascal and specific volume at 0.005 meter cube kg would be respectively. Try to calculate it. Is depends. This question is upon the same real gas, van der Waals gas equation. So take care of these things. It is given as kilo and kilo in both the constants. So you take care of that and calculate the answer. First will be the same because the ideal gas equation, the values is given are the same. So you need to calculate only for the real gas. So this is also GATE exam question. So extract out the given things. Pressure is given 10 megapascal. Volume is 0.005 meter cube kg per kg. Uh, R is 0.3 kilojoule per kg per Kelvin, and A is 0.18 kilo meter is 6 Pascal kg square. So this was the B is equal to 0.0014 meter cube per kg. Specific volume PM by RT. Uh, on the basis of the ideal gas equation, one of us. So which specific? Yeah, yeah. Uh, yes. PM by RT. You can say same. Uh, I'm not sure. PM by RT, how you are calculating it? You can directly put into, you can directly put because everything is per kg. You can directly put. Yes, yes. So we can, oh, okay. We have P is equal to, sorry, it is not working. We have van der Waals gas equation, P plus A by V square, P minus P is equal to RT. And we just need to put, we need to find out the temperature. So put the given values 10 raised to 7. So what we are having is 10 into 10 raised to 6 Pascal. Nothing but 10 raised to 7 Pascal. So 10 raised to 7 plus 0 0.18, 0.005. I think this is the volume is 005 meter cube, uh, which is the square into 0.005 minus the b value is 0.0014. Everything is given per kg, so it need not be, and R is zero point 0.3. And if you notice it, it in kilos, and this A value is also in kilo, means 10 raised to 3 into 10 raised to 3. And, so to calculate it, you'll get the temperature. So this is nothing but 3 point, it will come as nearly 3.6 into 10 raised to minus 3 divided by entirely the point raised to 10 raised to 10 raised to 206.40. Yeah, right answer. Fine. And the answer option is option 2046 B. So next question. The pressure of a gas changes linearly with volume from A to B as shown in figure. If no heat is supplied to or extracted from the gas, then change in the internal energy of the gas will be. So this is, I think, second last question. So what is given is the pressure of the gas changes linearly with the volume. And A to B is shown in the figure. If no heat is supplied to or extracted from the gas, so there is a dq. The change in heat is zero, and the internal energy of the gas will be. So we asked the internal energy what it will be. So what you are seeing is if you are given every time the pressure and volume graph, the change in you know that we know that the first law of thermodynamics, dq plus dw. So as you can see, the given question, the system is going from A to B, which means higher volume to lower volume, which actually why it's so higher volume to lower volume. So which means the compression is happening. So uh, compression means there is a work done on the system, which is the positive work. So the third option will be get cancelled. So how we can calculate is when we are given the PV graph, the area under the curve is nothing but the work done by the system. So we can calculate the area and you get the work. And as this dq is 0, the du will be the total work done by the system. You just calculate the area and calculate it carefully because this is 10 kilopascal, and we need to calculate first this rectangle, area of this rectangle, and this is 200 cubic centimeter. Okay, so your area of a rectangle will be 200 cc, which is nothing but in 1 centimeter is equal to 0.01 meter. So what we are having 10 raised to minus 6 meter cube into 10 kilopascal, which is 10,000, yeah, Pascal, and we'll get 2 into 150. uh, okay, sorry, my mistake here. Must be 150 because it is a 50 and 200. So 150, and if you get calculate into 10 is right, 10 raised to minus 6, 10 raised to 4. This is nothing but 1.5, and this area is 50. It's 14, and the base is 150. So area of the triangle 150 into 14 to half, 1 half base into height, which is nothing but the uh, and the same conversion factors will be applicable to here also. 10 raised to, let me write it another way, 150 into 10 raised to minus 6 into, let me charge the, I get 3 divided by 4 40. So what we'll get is 1520 here, 10 is to 15, 16. That was 3. Let me give it a joule. 3 joule. And the area under the curve is rectangle plus triangle with nothing but 3 plus 1.5. That's the thing, 4.5 joule. So the work is done on the system. So this positive, the answer will be 4. Last question. A sample of an ideal gas is taken from through the cyclic process ABCA as shown in figure. It absorbs 40 joule of heat during the part AB, no heat during BC, and rejects 60 joule of heat during CA. A work 50 joule is done on the gas during the part BC, and the internal energy of the gas at A is 1560, and the work done by the gas during the part CA is. So a sample of the gas is ideal and the process is ABCA, and so suppose it absorbs a 40 joule of heat during the part AB. We know this from A to B, it's absorb the 40 joule, which means heat is gained by the system. And no heat during B and C. B to C. B to C is no heat, which means and 60 joule of heat during C to A. So C to A, which rejects the 60 joule, means it's going outwards as a 60 joule. And a work done at 50 joule, a work 50 joule is done on the gas during the part BC. The part BC, if work is done on the gas, means it's adding the heat in the system in form of work, uh, and the internal energy of the gas uh, at A is, so internal energy at this point UA is 1560 joule, and the work done by the gas during the part C to A, we need to calculate work done by the gas to C to A. So as this UA is 1560, the total work, whatever the addition and subtraction uh, is happening inside the system, it should be goes to 0, because at the end it is coming at the same point A cyclic process, because your internal energy will not change. Delta is 0. So let's calculate what is coming inside and going out from the system. In the A to B, from AB, 40 joules added to the system, and we say Q in form of heat. And at B to C, 50 joules are added, and C to A, it rejects 60 joule, means it's negative. And they are saying work C to A, we need to calculate. So whatever addition of all this heat and work must be 0. So what you are getting the answer? Are you getting the answer? 40 plus 50 minus 60 plus WCA. This must be 0. This is 90 minus 60. plus WCA, which is nothing but WCA is 90 minus 60 is 30. If 30 goes that side, that's minus 30 joule. And the answer is minus 30 joule. C. Fine. Yeah, right. Sangeeta is right. Minus 30 joule is the answer. Okay. Thank you very much for the attending the session. We will meet the next week. Same number of problems I will include. So last section session we have completed nearly 30 problems, and now we are completing nearly 16 problems. So more and more we'll do the same both kind of problems from competitive and for the normal university examination. Thank you for attending this session again. Uh, we'll close the session. Thank you very much.